Tensor operator. In pure and applied mathematics, quantum mechanics, and computer graphics, a tensor operator generalizes the notion of operators which are scalars and vectors. A special class of these are spherical tensor operators, which apply the notion of the spherical basis and spherical harmonics. The spherical basis closely relates to the description of angular momentum in quantum mechanics and spherical harmonic functions. The coordinate-free generalization of a tensor operator is known as a representation operator. The general notion of scalar, vector, and tensor operators. In quantum mechanics, physical observables that are scalars, vectors, and tensors must be represented by scalar, vector, and tensor operators, respectively. Whether something is a scalar, vector, or tensor depends on how it is viewed by two observers whose coordinate frames are related to each other by rotation. Alternatively, one may ask how, for a single observer, a physical quantity transforms if the state of this system is rotated. Consider, for example, a system consisting of a molecule of mass m traveling with a definite center of mass momentums in the z direction. If we rotate the system by 90 about the y-axis, the momentum will change to x, which is in the x direction. The center of mass kinetic energy of the molecule will, however, be unchanged at p2/2m. The kinetic energy is a scalar and the momentum is a vector, and these two quantities must be represented by a scalar and a vector operator, respectively. By the latter in particular, we mean an operator whose expected values in the initial and the rotated states are x. The kinetic energy, on the other hand, must be represented by a scalar operator whose expected value must be the same in the initial and the rotated states. In the same way, tensor quantities must be represented by tensor operators. An example of a tensor quantity of rank 2 is the electrical quadrupole moment of the above molecule. Likewise, the octupole and hexadecapole moments would be tensors of rank 3 and 4, respectively. Other examples of scalar operators are the total energy operator, more commonly called the Hamiltonian, the potential energy, and the dipole-dipole interaction energy of two atoms. Examples of vector operators are the momentum, the position, the orbital angular momentum, L, and the spin angular momentum, psi. Fine print, angular momentum is a vector as far as rotations are concerned, but unlike position or momentum, it does not change sign under space inversion, and when one wishes to provide this information, it is said to be a pseudovector. Scalar, vector, and tensor operators can also be formed by products of operators. For example, the scalar product LS of the two vector operators, L and S, is a scalar operator which figures prominently in discussions of the spin-orbit interaction. Similarly, the quadrupole moment tensor of our example molecule has the 9 components: QH equals summation alpha kappa through alpha, R alpha, J minus R alpha 2 delta H. Here, the indices I and J can independently take on the values 1, 2, and 3 are x, y, and z corresponding to the 3 Cartesian axes. The index alpha runs over all particles, electrons, and nuclei in a molecule. Q alpha is the charge on particle alpha, and R alpha. I is the ith component of the position of this particle. Each term in the sum is a tensor operator. In particular, the 9 products R alpha, R alpha, J together form a second-rank tensor, formed by taking the direct product of the vector operator R alpha with itself. Quantum rotation operator. The rotation operator about the unit vector and defining the axis of rotation through angle thetas. $U equals \x left \frac 8 theta h bar hat math m c dot math j I at $, where j equal j, x j, y j. Z are the rotation generators, also the angular momentum matrices. $jx equals \frac h bar sqrt 2 begin p matrix 0 and 1 and 0 1 and 0 and 1 0 and 1 and 0 n p matrix quad j y equals \frac h bar sqrt 2 begin p matrix 0 and I and 0 I and 0 and I 0 and n 0 n p matrix quad j z equals h bar begin p matrix minus 1 and 0 and 0 0 and 0 and 0 0 and 0 and 1 n p matrix $, and let $white hat r equals $white hat r theta hat math and be a rotation matrix. According to the Rodriguez rotation formula, the rotation operator then amounts to $u equal 1 \, 1 backslash frac I backslash sin backslash theta backslash h bar backslash hat backslash math and backslash c dot backslash math j backslash frac 1 backslash cos backslash theta backslash h bar 2 backslash hat backslash math and backslash c dot backslash math j2 $. An operator omega is invariant under a unitary transformation U if omega equals U omega, in this case for the rotation hour. $backslash y dot backslash omega equal UR backslash dagger backslash y dot backslash omega UR equals backslash x backslash left backslash frac I backslash theta backslash h bar backslash hat backslash math and backslash c dot backslash math j. 8 backslash y dot backslash omega backslash x backslash left backslash frac I backslash theta backslash h bar backslash hat backslash math and backslash c dot backslash math j. $. Angular momentum adjuncts. The orthonormal basis set for total angular momentum is j, where j is the total angular momentum quantum number and meters is the magnetic angular momentum quantum number, which takes values minus j plus 1, j minus 1, j. A general state. Psi equals summation mj, in the space rotates to a new state j, by. Psi equals psi, using the completeness condition. I equals summation mj, we have psi equals a psi equals summation mj, introducing the Wigner D matrix elements. dr mj equals j, gives the matrix multiplication. Psi equals summation mjj, psi equals dj psi for one basis ket. $backslash overline j, angle equals backslash sum drj angle $. For the case of orbital angular momentum, the adjacent states L of the orbital angular momentum operator L in solutions of Laplace's equation on a 3D sphere or spherical harmonics. $y backslash lm backslash theta backslash phi equals backslash angle backslash theta backslash phi backslash l angle equal backslash sqrt 2 backslash l plus 1 backslash over 4 backslash pi backslash ln backslash over backslash l plus n backslash p backslash ln backslash cos backslash theta backslash EIM backslash phi where Pm is an associated Legendre polynomial is the orbital angular momentum quantum number, and meters is the orbital magnetic quantum number which takes the values minus plus 1, minus 1. The formalism of spherical harmonics have wide applications in applied mathematics and are closely related to the formalism of spherical tensors, as shown below. Spherical harmonics are functions of the polar and azimuthal angles, let 3d5 and theta respectively, which can be conveniently collected into a unit vector and theta, let 3d5 pointing in the direction of those angles. In the Cartesian basis it is $backslash hat backslash math and backslash theta backslash phi equals backslash cos backslash phi backslash sin backslash theta backslash math vx plus backslash sin backslash phi backslash sin backslash theta backslash math y plus backslash cos backslash theta backslash math easy $. So a spherical harmonic can also be written in y l m equals n lm. Spherical harmonic states m rotate according to the inverse rotation matrix ui minus 1, while l m rotates by the initial rotation matrix r. $backslash of a line backslash l m angle equals backslash sum and dm backslash l m angle backslash quad backslash of a line backslash hat backslash math n angle equal uvar backslash hat backslash math n angle $. Rotation of tensor operators. We define the rotation of an operator by requiring that the expectation value of the original operator $backslash y hat backslash math per dollar with respect to the initial state be equal to the expectation value of the rotated operator with respect to the rotated state. $backslash angle backslash psi backslash y hat backslash psi angle equals backslash angle backslash psi backslash y hat backslash psi angle $. Now is psi right arrow psi equals psi right arrow psi equals psi ur. We have psi u ra psi equals psi psi. Since psi is arbitrary, u ra equals a. Scalar operators. A scalar operator is invariant under rotations. Arcer equals. This is equivalent to saying a scalar operator commutes with the rotation generators. $backslash left equals $0. Examples of scalar operators include an energy operator, $y det e psi equal I h bar frat partial t psi potential energy V in the case of a central potential only ver t psi t equals v hour t psi t kinetic energy t $y det t psi math far t equal frat h bar 2 twom Apply to side math for t the spin orbit coupling $y det math c dot y det math s equals y det lx y det sx plus y det ly y det sy plus y det lz y det sc $. Vector operators. Vector operators, as well as pseudovector operators, are a set of three operators that can be rotated according to I equals summation. J. From this and the infinitesimal rotation operator and its Hermitian conjugate, and ignoring second order term in delta theta 2, one can derive the commutation relation with a rotation generator. Approximately I let a 210 f epsilon abc c, where epsilon is the Levi-Civita symbol, which all vector operators must satisfy by construction. As the symbol epsilon is a pseudotensor, pseudovector operators are invariant up to a sign, +1 for proper rotations and -1 for improper rotations. Vector operators include the position operator $y det math far psi equals math far psi the momentum operator $y det math p psi equal I h bar psi and pseudovector operators include orbital angular momentum operator $y det math fl psi equal I h bar math far times a bla psi as well the spin operator s, and hence the total angular momentum $y det math j equals y det math fl plus y det math s $. In direct notation, psi psi equals psi psi equals summation vi psi v psi, and since there's any quantum state, the same result follows. R equals summation Vr av a. Note that here the term vector is used two different ways, gets such as are elements of abstract Hilbert spaces, while the vector operator is defined as a quantity whose components transform in a certain way under rotations. Spherical vector operators. A vector operator in the spherical basis is v minus 1, where the components are $v plus 1 equals frac 1 sqrt2v x plus ivy quad v minus 1 equals frac 1 sqrt2v x ivy quad v 0 equal vz $. And the commutators with the rotation generators are equals qv q $left equals sqrt2v pm $left equals sqrt2v0 equals 0, where q is a placeholder for the spherical basis labels +1, 0, -1, and j plus or minus equals j, x plus or minus ij. While some authors may place a factor of 1/2 on the left-hand side of the equation and raise j plus or lower j minus the total magnetic quantum number meters by 1 unit. In the spherical basis, the generators are $j pm1 equals mp frac 1 sqrt2j pm quad j0 equal jz The rotation transformation in the spherical basis originally written in the Cartesian basis is then of qr equals summation q to qq asterisk q. One can generalize the vector operator concept easily to tensorial operators shown next. Tensor operators and their reducible and irreducible representations. A tensor operator can be rotated according to pqr equals pi rqj kinetic. Consider a dyadic tensor with components th equals a j. This rotates infinitesimally according to pqr equals pi rqj h equals pi I arc j. Cartesian dyadic tensors of the form $hat math t equals math vi y det I ottens math vj y det bj equals math vi ottens math vj y det I y det bj where and b are two vector operators. $hat math equals math vi y det I quad hat math b equals math vj y det bj $. Irreducible, which means they can be re-expressed in terms of R and B as a rank 0 tensor scalar, plus a rank 1 tensor and antisymmetric tensor, plus a rank 2 tensor a symmetric tensor with 0 trace. T equals T plus T2, where the first term $y at T0 ij equals \frac y at K y at B K3 delta ij includes just one component, a scalar equivalently written a B/3. The second $y at T1 ij equals \frac 1 2 equals \y at a includes three independent components, equivalently the components of a times B/2, and the third $y at T2 ij equals \frac 1 2 y at I y at B to J plus y at a J y at B I frac y at a K y at B K3 delta ij equals y at I y at B to J T0 ij includes five independent components. Throughout, delta ij is the Kronecker delta, the components of the identity matrix. The number in the superscripted brackets denotes the tensor rank. These three terms are reducible, which means they cannot be decomposed further and still be tensors satisfying the defining transformation laws under which they must be invariant. These also correspond to the number of spherical harmonic functions 2 plus 1 for equals 0, 1, 2, the same as the ranks for each tensor. Each of the reducible representations T, T2, transform like angular momentum eigenstate according to the number of independent components. Example of a tensor operator, the quadrupole moment operator, Q equals summation alpha 3 alpha j minus R alpha 2 delta ij. Two tensor operators can be multiplied to give another tensor operator. T equals V IW J in general. TI1IJ1J equals VI1IWJ1J. Note, this is just an example. In general, a tensor operator cannot be written as the product of two tensor operators as given in the above example. Spherical tensor operators. Continuing the previous example of the second-order dyadic tensor T equal a B, casting each of A and B into the spherical basis and substituting into T gives the spherical tensor operators of the second order, which are plus or minus 2 equals A plus or minus 1 plus or minus 1. $y at T 2 PM 1 equals frac 1 sqrt 2 left y at a PM 1 y at B 0 plus y at the 0 y at B PM 1 I $y at T 2 0 equals frac 1 sqrt 6 left y at the plus 1 y at B minus 1 plus y at a minus 1 y at B plus 1 plus 2 y at the 0 y at B 0 I $. Using the infinitesimal rotation operator and its Hermitian conjugate, one can derive the commutation relation in the spherical basis. Equals summation qj q2 equals summation qj equals 2 m equals qj, j equals 2, m equals q2. And the finite rotation transformation in the spherical basis is add q2 equals summation q to q2 stirs q2. In general, tensor operators can be constructed from two perspectives. One way is to specify how spherical tensors transform under a physical rotation, a group theoretical definition. A rotated angular momentum eigenstate can be decomposed into a linear combination of the initial eigenstates. The coefficients in a linear combination consist of Wigner rotation matrix entries. Spherical tensor operators are sometimes defined as the set of operators that transform just like the eigenkits under rotation. A spherical tensor TQK of rank K is defined to rotate into TQK according to U at QK UR equals summation Q to QQK asterisk QK, where Q equal K, K minus 1, minus K plus 1, minus K. For spherical tensors, K and Q are analogous labels to ammeters respectively for spherical harmonics. Some authors write TKQ instead of TQK with or without the parentheses enclosing the rank number K. Another related procedure requires that the spherical tensor satisfy certain commutation relations with respect to the rotation generators J, X, J, Y, J, D in algebraic definition. The commutation relations of the angular momentum components with the tensor operators are $left equals h bar sqrtk mpqk pmq plus 1 y at 2kq pm $1 equals letter 2 and 0 of qk for any 3D vector, not just a unit vector and not just the position vector. A equals a c x plus a y plus a c c. A spherical tensor is a spherical harmonic as a function of this vector, an indirect notation. TQK equals y letter 2113 equals k m equals car equals a k q. The super and subscript switch places for the corresponding labels k and meters q, which spherical tenses and spherical harmonics use. Spherical harmonic states and spherical tensors can also be constructed out of the Clebsch-Gordon coefficients. Reducible spherical tensors can build higher rank spherical tensors if a cone and b, q, where k2 are two spherical tensors of ranks k1 and k2 respectively. Then PQK equals summation Q of QK K Q of QK K K Q Q K1 B QK is a spherical tensor of rank. The Hermitian adjoint of a spherical tensor may be defined as TQK equals minus 1K minus QT minus QK. There is some arbitrariness in the choice of the phase factor. Any factor containing will satisfy the commutation relations. The above choice of phase has the advantages of being real and that the tensor product of two commuting Hermitian operators is still Hermitian. Some authors define it with a different sign on, without the, or use only the floor of. Orbital angular momentum and spherical harmonics. Orbital angular momentum operators have the ladder operators. L plus or minus equals L. X plus or minus IL. Y, which raise or lower the orbital magnetic quantum number meters by 1 unit. This is almost exactly the same form as the spherical basis, aside from constant multiplicative factors. Spherical tensor operators and quantum spin. Spherical tensors can also be formed from algebraic combinations of the spin operators S, XS, YS, C as matrices for a spin system with total quantum number J equal plus S and equals 0. Spin operators have the ladder operators S plus or minus equals S, X plus or minus IS, Y, which raise or lower the spin magnetic quantum number ms by 1 unit. Applications. Spherical bases have broad applications in pure and applied mathematics and physical sciences where spherical geometries occur. Dipole radiative transitions in a single electron atom alkali. Dipole radiative transitions in a single electron atom alkali. The transition amplitude is proportional to matrix elements of the dipole operator between the initial and final states. We use an electrostatic spinous model for the atom, and we consider the transition from the initial energy level En at 2113 to final level En. These levels are degenerate since the energy does not depend on the magnetic quantum number meters or m. The wave functions have the form psi NLMR theta, let 3d5 equals r NLR y lm theta, let 3d5. The dipole operator is proportional to the position operator of the electron, so we must evaluate matrix elements of the form NLR and LM, where the initial state is on the right and the final one on the left. The position operator R has 3 components, and the initial and final levels consist of TWO latitude 113 plus 1 and TWO latitude 113 plus 1 degenerate states, respectively. Therefore, if we wish to evaluate the intensity of a spectral line as it would be observed, we really have to evaluate THRE TWO latitude 113 plus or any TWO latitude 113 plus 1 matrix elements. For example, 3 times 3 times 5 equal 45 in a 3-to-right arrow-to transition. This is actually an exaggeration, as we shall see, because many of the matrix elements vanish, but there are still many non-vanishing matrix elements to be calculated. A great simplification can be achieved by expressing the components of R, not with respect to the Cartesian basis, but with respect to the spherical basis. First we define $RQ equals \hat \math pq \c dot \math var $. Next, by inspecting a table of the y latitude 113m's, we find that for latitude 113 equal 1 we have $R y11 \theta phi equals r sqrt frac 38 pi sin theta ea phi equals sqrt frac 34 pi left frac x plus e sqrt 2 I $R y10 theta phi equals r sqrt frac 34 pi cos Caesar equals sqrt frac 34 pi z $R y1 theta phi equals r sqrt frac 38 pi sin theta ea phi equals sqrt frac 34 pi left frac x e sqrt 2 I where we have multiplied each y1 by the radius r. On the right-hand side, we see the circle components are Q of the position vector r. The results can be summarized by $RY 1 backslash theta backslash phi equals backslash SQRT backslash frac 34 backslash pi RQ for Q equal 1, 0, minus 1, where Q appears explicitly as a magnetic quantum number. This equation reveals a relationship between vector operators and the angular momentum value let to 113 equal 1, something we will have more to say about presently. Now the matrix elements become a product of a radial integral times an angular integral. $backslash angle n mod cube NLM. Angle equals backslash left backslash in 0 backslash in R2 doctor RN asterisk RNLR. I backslash left backslash SQRT backslash frac 4 backslash pi 3 backslash int backslash sin backslash theta d backslash omega ym asterisk backslash theta backslash phi y1 backslash theta backslash phi ylm backslash theta backslash phi at $. We see that all the dependence in the three magnetic quantum numbers m, q, m is contained in the angular part of the integral. Moreover, the angular integral can be evaluated by the 3y latitude 1 formula, whereupon it becomes proportional to the Cauchy-Gordon coefficient, am lonum. The radial integral is independent of the three magnetic quantum numbers m, q, m, and the trick we have just used does not help us to evaluate it. But it is only one integral, and after it has been done, all the other integrals can be evaluated just by computing or looking up Cauchy-Gordon coefficients. The selection rule m equal q plus meters in the Cauchy-Gordon coefficient means that many of the integrals vanish, so we have exaggerated the total number of integrals that need to be done. But had we worked with the Cartesian components Ri of r, the selection rule might not have been obvious. In any case, even with the selection rule, there may still be many non-zero integrals to be done now, in the case 3 right arrow top. The example we have just given of simplifying the calculation of matrix elements for a dipole transition is really an application of the Wigner-Eckart theorem, which we take up later in these notes. Magnetic resonance. The spherical tensor formalism provides a common platform for treating coherence and relaxation in nuclear magnetic resonance. In NMR and EPR, spherical tensor operators are employed to express the quantum dynamics of particle spin by means of an equation of motion for the density matrix entries, or to formulate dynamics in terms of an equation of motion in Liouville space. The Liouville space equation of motion governs the observable averages of spin variables. When relaxation is formulated using a spherical tensor basis in Liouville space, insight is gained because the relaxation matrix exhibits the cross-relaxation of spin observables directly.